The Jacinto 7 processors implement multiple hardware features to facilitate virtualization, which is one popular method to achieve isolation between software tasks. Virtualization hardware involves a combination of central address management and also specific isolation features embedded in IPs such as PCIe, GPU, and the display subsystem. Although some of these features are centralized, almost all core and IP on the device can take advantage of using virtualized data space directly or via the DMA. In this section, I will give an overview of these hardware features. The primary cores on the SoC implement memory management units, which are the traditional method for mapping physical to virtual memory space for security and address containment between tasks. Jacinto 7 cores implement a two-stage MMU to facilitate multiple virtualized OS instances. Additionally, multi-stage I/O MMUs are provided to allow data I/O peripherals to be directly programmed to use the virtual address space. This allows for more efficient use of peripherals as the virtual machines can directly program them. There are two I/O MMUs available in the Jacinto 7 system, the ARM v3 compliant system MMU or SMMU, and the TI Peripheral Virtual Unit or PVU. The SMMU may be used for standard software and hypervisors, while the PVU can concurrently be used to virtualize memory space used by real-time peripherals such as display or capture, which can be challenging to service effectively with SMMU due to latencies. Additional real-time scatter-gather access is provided by the Page-Based Address Translator, or PAT, which can be used in conjunction with PVU. Several peripherals also have direct virtualization features, such as the PCIe controller, which supports the PCIe standard Single Root I/O Virtualization Standard, or SRIOV, leveraging the SMMU or the PVU. Both the display subsystem and the GPU support virtual ownership of resources within the IP. The DSS resource ownership is set up statically, while the GPU has a dedicated microcontroller to dynamically allocate and manage resources as tasks are requested by each virtual driver. Both the SMMU and the PVU and PAT models of virtualization can coexist concurrently in the system. The UDMA concept of flows can also be leveraged by the Ethernet controllers to maintain separation of multiple networking data streams. Together with access permissions enforced by the firewalls and security components, these virtualization components and features can be used to build a robust, high-performance mixed system where real-time is maintained and cores are contained to their own resources. The Jacinto 7 processors integrate many key features centered around security. From the DMSC acting as an isolated security master, to hardware crypto engines in both the main and safety MCU domains, to multiple embedded security features on various IPs across the device. Finally, to full endpoint firewall protection across the device for memories and peripherals. Security is truly an integral part of the overall SoC architecture. As automotive systems become more and more connected and safety requirements are going up, security is more vital than ever in the automotive application space. This section will give a high-level overview of the various features which implement security on the Jacinto 7 SoC. Jacinto 7 supports both secure boot and runtime security. One-time programmable or OTP fuse ROMs allow the option for customer securable devices. The basic premise of the architecture is that the DMSC is the primary security master in the system, owning all firewall configurations, secure keys, and sensitive secure resources. All requests to DMSC for firewall or resource configuration must go through a secure messaging mechanism to ensure DMSC can fully enforce the security policy of the system. All master access credentials are controlled by DMSC via Initiator Security Control or ISCs. Endpoints and shared memories are protected through a variety of firewalls, from region-based firewalls to channelized firewalls, depending on the specific resource. Various cryptography algorithms are implemented in hardware in central crypto accelerator resources located on both the main domain and the MCU safety domain. The UDMAs can route data to and from these resources, but secure UDMA flows are controlled by DMSC to only allow access from authorized cores or tasks. Finally, in addition to these central resources, various cores and IP peripherals also implement their own security features. These include standard embedded crypto for I/O peripherals which require it, as well as system features such as GPU, DSS, and Ethernet for secure content support and secure stream support. Also, standard ARM Trust Zone is supported for a secure execution environment on the A72. Power management is critical in automotive applications to stay within the thermal envelope of the system. Jacinto 7 implements multiple features and strategies to control power both statically and dynamically. The DMSC provides central control for the various power modes of the device. However, from clock gating to power domains and thermal monitors, the relevant features to control power really permeate the entire device architecture. In this section, I will give a brief overview of the key power management features implemented throughout the architecture. The Jacinto 7 processors implement multiple independent voltage domains which facilitate different power modes and strategies for reducing overall power on the device. The primary CPU domain supports adaptive voltage scaling, or AVS, to reduce leakage. Many of the major cores and accelerators support independent power domains so they can be shut off completely when not in use to save power. Fine-grained clock control, dynamic frequency scaling, and dynamic clock gating all facilitate reduction of active power while maintaining required system performance. Multiple voltage and thermal sensors distributed across the device allow for monitoring of the SoC power systems to throttle system performance dynamically as needed to stay within the system power envelope. Multiple SoC power modes are supported which allow management of system power in various scenarios. These range from idling cores to shutting off unused power domains to shutting off the entire main voltage domain in MCU-only mode. MCU-only mode is useful for booting only the safety MCU without having to bring up the entire main domain. Finally, for the lowest power modes, the entire device can be shut off except for the DDR/I/O, which can then be used to maintain self-refresh mode on the external DDR. This is useful for a quick resume of a high-level OS from a very low power state.
Thank you for watching this training. For more information, refer to the links shown. For questions about this training, go to the processor forums at ede.ti.com.